Good evening, everyone. Today we will be discussing a topic called as built-up columns. So, what do we mean by built-up column? It's a column which has more than one member. Now we can see here. This is the top view of a built-up column, which is like comprising of two channel sections. We can see here. This is one channel section, and this is another channel section. Okay, and these channel sections are what? The sections which generally have the cross section of the shape of a C. And here we just given an example that it is comprising of a channel section which is called as ISMC 350. So you can look into ISMC 350 in the steel table. Now we can the channel sections, these two channel sections are placed in a way which we call as back to back. Back to back means the back of the channel sections are facing each other. Now the how can we look into it? You see, this is the back of this channel section and this one is the back of this channel section. So since these two are facing each other, we can say that this is a back to back placement. Now the spacing of the spacing between the back part of the channel sections is termed as S. Okay, and we should also see here that if we look into the individual channel sections, suppose there are two channel sections here. So if we look into this single channel section, it has its own y-axis. You can see that this in the steel table also, and it will have its own x-axis also. Okay, in some books it is written as z-axis. It's the same thing. Okay, just the names are different. Now here also in this channel section, it is having its own y-axis and it is having its own x-axis. And now when they are together, they will have their combined y and x-axis, because when we look into the built-up column, we will take into account the whole column, the performance of the column as a whole. Now if we look into the built-up column, it will have its y-axis like this and x-axis like this. So this y dash and x dash is the axis of the built-up column, and this y-axis and this y-axis are the axis of the individual columns or the individual sections, and this x-axis and this x-axis are for the individual sections, and if we place them, it gets merged. It's logical if we look into the placement, since you see here this x-axis will be for this section and this x-axis will be for this section. So when we place it like that, since they are passing through the same way, so they will merge. But here this channel section has a y-axis here and it is having a y-axis here, so they will not merge. So obviously it will the combined y-axis will be placed here. Now the strength of a built-up column is obviously much more higher than the strength of a column which is made up of a single member. Okay, and in the design problem, what we do is we are given a load and we have to determine what type of channel sections we need to place. Okay, either back to back or 2 to 2. What do you mean by 2 to 2? 2 to 2 is way in which the 2 to 2 position is the way in which the channel sections are placed when their toes are facing each other. If I draw it, it will look like this. So this is a situation of a toe to toe. It means here you can say this is the back of this channel section and this one is the back of this channel section, and they are not facing each other. Instead, these toes are facing each other. So that is called as toe to toe. Okay. And this one is called as back to back. Now, uh, for heavier loads, we will be designing built-up columns, and for smaller loads, we will be designing columns having just one member. So in design problems, what the situation will be that you will be given a load, and you for that load you have to determine what type of sections uh, shall be used to make up the built-up column. So we have to determine the section basically. Okay, and then when we determine the section, we cannot place it just like that. Okay, if we just place it just like that in this manner, they will not be acting as a single entity. So if they have to act as a single entity, then we have to connect them. Okay, how do we connect them? We connect them using some members, which is called as lacing. So that part we will be going step to step, step by step. Now uh, uh, what I will do is we'll be taking one problem, one situation, and parallelly we will be learning about the concepts and theories that are behind built up columns. So if I again go into the revision, I'm just saying that built up columns are stronger columns. They are obviously stronger than columns made up of one member. That's why they are used for higher loads. Okay, and in design problems for a given type of load, we have to determine the sections or the members that will uh, make up the build-up section. And also one more thing that I would like to say is that when they are placed either back to back or toe to toe, we have to determine the spacing. That is one very important criteria. Okay, so that we will look into. Okay, as we proceed. And one thing that I want to repeat once again is that we have to be very clear about the axis. This y-axis and this x-axis, just look into this part. This y and this x will be for this section, and this y and this x will be for this section. And for a combined, when they will act as a combined, their y-axis and x-axis will be this one and this one. Okay, and the combined column, build-up column's x-axis gets merged with the x-axis of the individual sections, and the y-axis of the built-up column does not get merged like that. Okay, you can see it's logical, and so they are located at different positions. Now let us take one problem. Let us take a situation where the load given is 1200 kilonewton. Okay, and the length of the column is given, which is 9 meter. Okay, so you can write it down. So 1200 kilonewton load is given to us, and the length of the column is given as 9 meter, and it is said that the column is fixed at both ends. That is the boundary condition. Okay, so fixed at both ends, you can write it down. Okay, so these are the situations. Load given, length of the column is given, boundary condition is given. Then we are being told to design the built-up column. Okay, and it is also told to us that the columns are the sections are placed back to back. Okay, so we have to take into account this situation, not this one. Okay, So let us start. When we are being told that the column is fixed at both ends, then we have to take into account the coefficient which is there for the boundary condition when the column is fixed at both ends. So what will be the value of the coefficient? The coefficient which is k is equal to 0.65. Okay. So when the column is hinged at both ends, it is 1, k equal to 1. When the column is fixed at one and hinged at the other, then there will be different value. And when the column is in such a way that it is fixed at one and then free at the other end, then k will be different. Okay, so you should remember in the values of k for various conditions, you have to use it, okay, in various problems where the boundary conditions are different. Okay, so you have to remember those values of k. So it is there in the IS code also, so please look into it. Okay, the condition that is given to us is we have discussed this 1200 kilonewton load, 9-meter length, and the column is fixed at both ends. So let us first convert the kilonewton load into Newton. So it will be 1200 into 10 to the power 3 Newton. Then what we will do is we will assume a design compressive stress, which is FCD. Okay, FCD. Now FCD, when we assume, there is no specific rule in any book about what value that you need to choose. Here I am choosing 125. So you might ask me why I am using 125 Newton per mm square. I will just say that it depends on experience. There is no specific rule. You see, this obviously the design compressive stress will be more for a built-up column, isn't it? Rather than a column having one member. For a column having one member, if you ask me what FCD you will choose for design, what FCD you will assume for design, I'll say that I will be assuming 80 to 100. Okay, but still, if you ask me then also that why are you using 80 to 100 for columns having one member, I will say that it is just based on experience. Okay, as you keep on doing problems, you will be having an idea about how much FCD to choose for what type of columns. Okay, so as we keep on doing problems, you will automatically have that idea. Okay, so this is simply based on experience. So now, as we have chosen FCD is equal to 125 Newton per mm square, design compressive stress. So one more thing we need to take into account is the Fy, okay, for steel. Since it is a steel design, so Fy we will be taking 250 Newton per mm square. Okay, so this is a plate material. Normally it will be given. Okay, but if it is not given, then you have to take this value Fy. Okay, so now FCD is given, load is given. Let us take it as a factored load. This 1200 kilonewton, let us take it as a factored axial load. Okay, if it is taken as a factored axial load, then obviously we don't have to multiply 1.5 again. So let us take this P as a factored one. So since we don't have to take 1.5 a multiplying factor again, so now let us find out the area required. Area required will be how much? Load divided by the design compressive stress. So let us calculate. So what will be the value? What will be the value? 1200 into 10 to the power 3 divided by 125. It will be how much? 9600 mm square. So we have got area required. Now for this area required, we have to look into the steel table and we have to find a section using the steel table which is having a higher area than 9600 mm square. So you see both in this is one example of a what build-up column having two channels back to back. Okay, so we'll obviously be designing a section similar to this one. So now the area whatever we will be taking, it should be more than 9600. So that area will be the combined area of these two. Okay, so we will not take like the area of a single section as more than 9600. If we'll take the area of the whole combined area of the two channel sections more than 9600. So if that is the condition, then if we divide 9600 by 2, what we get? See, if the area should be 9600 in total, then area of one channel section should be 4800. So if the area should be greater than 9600 in total, then the area of one channel section should be greater than 4800. So let us find one channel section whose area is greater than 4800. Obviously, and then what will happen if we combine them both? It will be more than 9600. So let us look into the steel table. So I can take it, there's a coincidence that if we look into ISMC 350 itself, this one ISMC 350 in steel table, we see that the area of ISMC 350 is 5366 mm square. Okay, so 5366 mm square. Obviously it is greater than 4800. Isn't this 5366 is greater than 4800? So obviously if we take two ISMC 350 like this one and this one, their combined area will be greater than 9600. So that is what we want. So let us go with this one only, ISMC 350. Now as we have decided here ISMC 350, so we have to write down all the values that we get for that section in from the steel table. Whatever value we get, we have to write that down. So let us write it. So from the steel table we can see that this H is this one is 350, B is this one is 100, thickness of flange is this one, so this is 13.5, thickness of web is this one 8.1. Okay, along with the dimensions, we should also write down the moment of inertia, that we get for the individual. These are all individual values. Okay, please keep that in mind. All right, so for this one it's 350, 100, 13.5, 8.1. Here also 350, 100, then 13.5 and 8.1. Now we let us write down the moment of inertia values for each section. So here this section has y-axis and x-axis. Okay, so the moment of inertia of each section about x-axis will be ixx, you see here we have to also write the radius of gyration. So we have written the radius of gyration about x and y axis for the individual sections, and also the moment of inertia about both axes. Now if we look into the difference, we see that the moment of inertia about y-axis is less compared to the moment of inertia about x-axis, and that's why obviously the radius of gyration about y-axis is lesser than the radius of gyration about x-axis. Ryy is less than rxx, obviously, because Iyy is less than ixx, and vice versa. Okay, now why we are saying that? Because radius of gyration is proportional to moment of inertia. Now you see, if a section is having a lesser moment of inertia about a certain axis, that means what? It is weaker about that axis. So for individual section, let us not go into the bigger picture right now, built up column. Let us just concentrate on the individual part. If this section y-axis Iyy is lesser than the moment of inertia about x-axis, that means this section is weaker about y. When you will give a load on this section, it will try to rotate like that. Once again I am repeating, concentrate on this section. Okay, this is universal. In this section, this is the y-axis and this is the x-axis. if the moment of inertia of this section is, it's not if, it is in real, the Iyy value, moment of inertia about y-axis is less than the moment of inertia about x-axis. So this section is weaker about y-axis. So if we give a load on this section, what it will do is it will try to rotate like this. That means about yy it will rotate because it is weaker. If it would have been in such a way that the ixx is lesser than iyy, then we can say that this section is weaker about x. Okay, if the ixx is lesser than iyy, okay, then what would have happened? It is weaker about x, then it would have rotated in this manner about xx. But that is not the case here. The case here is that the iyy value is lesser than ixx, so it is weaker about y. Okay, and it will, whatever load we get, it will rotate like this. Same goes for this one. Okay, so now let us go into the bigger picture. The bigger picture is that this is the y-axis of the built-up column. This is the x-axis of the built-up column. These were the y-axis of the individual columns, and these are the x-axis of the individual columns. Now, if you want to make a column stronger about both axes, what we need to do? Strength is proportional to the moment of inertia. Okay, so as we can see here, I'm repeating this again and again. Iyy value is very less compared to ixx, so strength about yy is less. If iyy would have been equal to ixx, what could we have said? If iyy would have been equal to ixx, then we could have said that the strength is same in both axes, because moment of inertia is proportional to strength. So isn't it good if we can design a column, a built-up column, whose moment of inertia about this y dash, and moment of inertia about x dash is same, not exactly same but almost equal, then we would ultimately be designing a built-up column having equal strength in, almost same strength in both direction. So why not design a column like that? That would be a very good column, isn't it? So that should be one aim that we need to consider. Okay, while designing a built-up column, we need to we have to design it in such a way that the column is strong about both axes, about y dash and x dash. We cannot do anything about the individual sections, because the individual sections is already having their default iyy value and ixx value. This also is having its default iyy and ixx value. We cannot do anything about it. It is already there, but we can modify the moment of inertia about this y dash and x dash in such a way that the values become same about of the moment of inertia about this axis and this axis. So how can we do that? We have to use this as value. Using this as value, we have to play with it such that we can get a moment of inertia value which is almost same in both directions. So that is our purpose, first purpose. This is just the beginning. Okay, So I'm just saying once again that when you are designing the build-up column, we have to design it in such a way that the moment of inertia about y dash and x dash should be almost same. It may not be exact, but it should be almost same, so that the strength of that build-up column becomes equal in both the directions or both the axes. So for that, the main thing that will come into play is this value. Okay, so what we will do is we will continue with the further steps in the next class. So stay safe, wash your hands regularly, let us defeat coronavirus, and let us hope that our classes gets like our classes resume soon, and let us not make coronavirus the winner. Let us not I can say that let's not get scared. Also, let us not panic. Okay, thank you very much.